So having fed the values through the network forwards, we now need to work backwards and work out how we can optimize these weights to improve on our error. Just looking at this, actually that equation there is not quite right, because that one is not the sum times the weight times the inputs, it's effectively the weight times the output of the hidden neuron, just to be clear. So I've started up the formula auditing tool, which you can do from here in my version of Excel. And what this allows me to do is to kind of work out either what the field's dependent on, what the cell's dependent on, or what cells are dependent on it. So these two buttons, trace dependence and trace precedence, this will show me what values depend on this cell, and this will show me what values precede this cell. So what values is this dependent on? So if we use this one here, we can follow the route of this weight as it goes through the neural network. So we can see, and we know this because we type the formulas in, we can see that it goes into the sum of the weights times the outputs of the previous layer. It then gets fed into this net, right, which is effectively just adding in the bias. We then feed that into the out value, which is the sigmoid function of the net. We then feed that into the error calculation, which is subtracting it from the target, squaring it, and then dividing it by 2. We can also do this the other way around. We can go to the error and we can look and see the same thing the other way around. So we can see the error is based on the output is based on the ignore that one because that's just showing you the target coming in. The output is based on the net is based on the bias, the bias is based on the net is based on the sum plus the bias, and then the sum is based on the weight. So in order to do this, I'm afraid we're going to have to do some calculus. So we're going to have to work out the gradient of the graph, and the way that we do that is using differentiation. Now I don't want to dwell too much on the mathematics, but basically most of what we're going to do is fairly simple. We're going to base it on the power rule. The power rule simply states that if we have a formula that is y equals x to the n, then the derivative or the gradient of that equation is n to the x minus 1. Now I'm avoiding using all the complicated notation with deltas in it to keep things simple. This is just the formula and this is the derivative or the gradient. Now we need to use two specific use cases of that power rule. One is where y equals x squared, and if we just apply the power rule, basically we reduce the 2 down to a 1, so we get x to the 1, which is just x, and then the 2 comes down in front of the x, so we get 2x. Similarly, if we have y equals ax, then x is x to the 1, as we just talked about. So if we take the 1 down, well, it doesn't make any difference. It's 1 times a, which is just a, and x becomes x to the 0, and x to the 0 is 1. So here's the two basic rules that we need to know. Y equals x squared is going to 2x, y equals ax just drops out. And in fact, if I were to add a constant onto here as well, plus c, oh, not like that though, because the constant's not dependent on x, then that doesn't have any effect on the gradient. So the derivative of y equals x squared plus c is just 2x, and the c disappears. Right, that's as much of the calculus I'm going to cover in this video. So what do we need to do? We need to work out what the gradient of these graphs is. Now, as we've seen, we've got basically 3 calculations. We've got multiplying the weight times the output of the previous node, or the input if we're over there, which is this calculation here, which is G13 times K10. We then take the sigmoid function of that as our second formula, and our third formula is this one here. Now what we could do is we could try and combine all of that into one single formula and try and differentiate that, but that's two problems with that. Firstly, this is fairly complicated, and by the time we've fed all these values into here, we might end up with something a little bit difficult. But also, we can do it simpler by using something called a chain rule, which simply states that if you've got something like this where you've got a value from here going into a value here, and that value going into there, and that value going into there, then what you can do is you can calculate the derivative of each step, multiply them together, and you'll get the end result. And that kind of makes sense, that if you've got a formula that gives you a gradient 2, and you put that into a formula that has a gradient 2 on there, that the gradient of the whole thing will be 4. So that's what we're going to do. So we're going to work out how we get from there to there. And here we've got the formula. The formula is this thing here. So let's just stick that there just so that we can see it. Oops, not like that. This is what we had the problem earlier. So we're trying to differentiate this with respect to the output, because it's the output that's going into this, which is M13, which is this one here. So we need to differentiate this with respect to M13. So pretend our M13s are x. M13 is squared, and we know from the power rule that when we do that, we take the 2 down here and we reduce the factor by 1. So that 2 will go down to a 1, and the 2 will come over here. And you can see now why we stuck this 0.5 in, because 2 times 0.5 is 1, so that makes that disappear. This 2 goes down to a 1, which basically means we can get rid of it, because to the power of 1 is just the same as having it without any power. But because this is minus M13, there's a minus that drops out at the beginning here. So the derivative of that is basically minus O13 minus M13 minus O13 minus M13. Really, it's a string, not as a value. Okay, so that's relatively simple. Now, the thing to bear in mind here is that we actually took the target minus the output to work out the error. We could have just as easily done it the other way around and had the output minus the target. Because we're squaring it, it doesn't matter whether it's minus 3 squared or plus 3 squared, it's still going to give you 9. So if we'd done that the other way around, then, well, let's do it. M13. Now, when we differentiate that, the 2 comes down and wipes out the 0.5, but now the M13 is positive, so it doesn't need to have the negative sign on the front, and basically that turns out to be M13 minus O13. And here, all the way through, M is the output, and O13 is the input. So I can write that equally as either minus the target minus the output, or just the output minus the target. And you'll see, depending on the literature that you read, sometimes it's done this way around and sometimes it's done that way around. Arguably this one's easier to think about. I've got into the habit of using this one. It will both give you the same result. Right, so basically that means that we've worked out the gradient from there. Oops, sorry. The gradient from there to there is just minus, so let's think of some notation. So this is going from out to error is the minus the target minus the output. So minus the target minus the target minus the output. Good, we're off and running. So we've got the first stage of our partial derivative, which is the first step here. The next step that we need to look at is going here. Now remember, this was a fairly complicated function, and it actually not too difficult to differentiate, but I'm not going to cover that here. I might cover that in a separate video because it is a bit more involved and ugly. But by some mathematical coincidence, right, when you differentiate this, you end up with a formula based on M12, which is this field here, which is the input to the calculation. But by some strange coincidence in mathematics, I think it's a coincidence, you can actually express the derivative in terms of the result of the calculation. And you will always often find that that equals the output. So let me get rid of those. Equals the output times 1 minus the output. Now I'm conscious that I've just dreamt that up out of thin air, but there's plenty of documentation, and I might make a video on that if I get time, to describe how do you get from the differentiator of that to that. So that gives us the net to the output. So the final step, remember where we were, we're going back from here, so basically this step here, although I've written it down as 3 separate steps with taking the bias and summing it in, basically all this is doing is taking the weight 5 times the output from here, adding the bias. So the bias is a constant, we can ignore it. So effectively all we've got here is we've got weight 5 times output from hidden layer 1. So we do need to differentiate that now with respect to weight 5, which basically means that this bit just drops off. So we end up with the weight of, so the value of out. Okay. I'm going to save that though for a little bit later on. So we remember that we've still got the value of out to multiply into here, because what I'm going to do is I'm going to create kind of a partial way through this calculation by multiplying those two things together. Because that's generally done and called delta. Just while I'm in here, I'm going to change the color of this, because I did say I was going to use that mauve color for the forward pass. I'm going to use this color. This color for the backward pass, just so we can see these numbers are forward and these numbers are backward. Right, so this is the delta. Now the reason we keep this number as a separate number is we're going to find as we go on that we can reuse this number lots of times in the future. Here we've only got one weight, but if we had lots of different weights coming into this node, they would all be just start from this point and multiply themselves by the corresponding input. So we can reuse this over and over again. So in order to make life easier going forward, I'm going to work that out as a delta. Right, and then what I can work out is the delta in weight 5. So the overall gradient from here back to here is basically that value multiplied by that value. So we can do that by equals the delta times the output of the previous node. So that gives us our gradient. So that is the gradient of the graph of all these calculations with respect to weight 5. So effectively we can see that we are negative. So we can see that, remember looking at the graph, so weight 5 with the value of weight 5 is 0.8, roughly speaking. 0.8 is here. Yes, the gradient is negative. Now remember here that the values that we've got on the y-axis are very small compared to the x-axis. If we actually change the values of this y-axis here to be similar to the to here. So let's make it go from, instead of 0 to 0.0016, we'll make it go from 0 to, say, I don't know, 3. So it's a similar kind of scale to the x-axis. You can see that it's pretty flat, right? And that's why when we look at the result of our calculation of the gradient, it's come out as a pretty low number, because the gradient of the graph that we're looking at is pretty flat. But it does confirm that we are a negative gradient because the line's coming down this way. So we take the gradient here. It looks something like that. It's a negative gradient. Because it's negative, we know we need to move right. We need to make the number bigger. Now, what we could do is we could just work out that it's a negative gradient and just add a number onto it to make us step into that direction. But what generally we do is we take actually the value of the gradient and we take a step proportionate to the size of the gradient, which means that if you're way up here, right, and you've got quite a steep gradient, then you take a bigger step, and when you get down here and you're at a lower gradient, and you kind of step smaller and smaller steps to get to the minimum. So what we actually do is in here, we would take weight 5 and we actually subtract the gradient. Okay, by subtracting a negative, it makes it a positive, which makes the number go bigger, which is what we wanted. We've taken into account the direction of the gradient, and we've taken some proportion of the size of the gradient to make the step bigger or smaller. But rather than just do that, what we normally do is we set a rate function so that we can adjust how much of the gradient to take into account, or kind of the size of the step. We can make the step larger or smaller relative to the gradient. I've just set this gradient to 0.5, so I can just take that and multiply it additionally by that rate. And I'm going to hit F4, which will put $signs in front of that, which means whenever I copy this value anywhere, it won't move. I'm not quite sure I'm going to need that, but it's there just in case. I don't know why I put that quite so high up. I wanted to keep everything together. So there is my change in weight 5. So what I can do now is I can adjust weight 5 by saying I want a new value which is equal to weight 5 plus the change that I want. Sorry, minus. Remember, you've got to take it and subtract it. That was the whole point. Minus. Because subtracting a negative makes it a positive, which means we're making the number bigger. So we're going to go from 0.815 to 0.816. So we're going to go from 0.815, a tiny little step this way, 0.816, so we move down the hill. Only a little bit, but we've moved down the hill, which is what we were trying to achieve in the first place. So that's basically differentiation of this first neural node. I'm going to do a bit of tidy up, and then we'll pause and we'll take on how we calculate the gradient for weight 1 so that we can continue and work out the new value of weight 1.